Welcome to today's topic. Fraunhofer diffraction at N-slits. That is also diffraction grating. What is grating? For example, in the Fraunhofer single slit experiment, we have taken a slit with the width of A. In the double slit experiment, we have taken one more slit. The width of the slit is also A. Those two slits are separated with distance, that is B. Okay, this is double slit. Suppose if you take another slit, that is called as triple slit. Like this. Suppose if we take any system, if the system is consisting of large number of slits, that arrangement is called as diffraction grating. How it was constructed? Initially, that was constructed by Fraunhofer by using fine wires. He has taken some frame and that he has placed some fine wires like this. And also he was allowed the light to pass through them. These lines are acts like a opaque barriers, and in between these wires the light is passing. That means these are acting like a slit. Here one thing we should be remember, that is the width of the each slit is same. And also width of the opaque barrier is also same. Further, the diffraction grating was constructed by using a transparent medium. They have taken the transparent medium, on that there is a mission drawn lines with the diamond pointer. The diamond pointer is drawn the lines like this on the transparent medium. Okay, there is a screw. The screw is adjusting. That means whenever the groove has drawn, it was adjusted or it was moved like that. So like that. These grooves are acts like a opaque barriers. Why they are behaves like a opaque barriers? It's simple. Suppose if we take a transparent glass plate, and that if you take a stone, and that if you draw a line, so automatically the polished surface becomes a rough surface. As we know that the rough surface will not be allow the light to pass through them. In between the scratch lines, the light can pass. The light where the light is passing, that can be called as a slit. Like that, he was constructed the grating. Actually, the excellent grating is having a number of lines per inch is 30,000 lines. How many lines? 30,000. 30,000 lines per inch. That means that equals to 1 inch means 2.54 centimeters. That means in the 2.54 centimeters, there were 30,000 lines were drawn with the diamond pointer. Wherever we are drawing the line acting like a rough surface, that means that is acting like a opaque barrier, that is not allowing the light. In between the undrawn position, that is acting like a slit, it is allowing the light to pass through that. In our laboratory, we are using the diffraction grating to determine the wavelength of the source of the light. To determine the wavelength of the source of the light, in our laboratory we are using that grating. How it was constructed? Is, okay, they have taken a masterpiece of the grating, and that they have poured cellulose acetate. It is a solution. That solution has poured on this good masterpiece. So they have dried that one. After they have dried that one, so they have taken that layer and that is placed in between the two glass plates, transparent glass plates, and taken the plaster also. Like that, in our laboratory, diffraction gratings were constructed. Usually in our laboratories, we may use 15,000 lines per inch. 15,000 lines per inch. This type of gratings we are using to determine the wavelength of the source of the light. Okay, how we can determine the wavelength of the source of the light? What is the formula? We will derive that formula. Regarding that one, we have to take a system of a part of grating, a section of grating, a section of grating. Like this. The width of the each slit is A. Width of the each slit is A. This is A. And the opaque barrier is B. These are the slits, first, second, third. That means we may name this one as A, B, C, D, E, F, G, H, I, J, K. This is a section of diffraction grating. Okay, we are allowing the light to pass through them. AB is a slit. The width of the slit is small a. BC is the opaque barrier. The width of the opaque barrier is B. A plus B is called as here grating element. Also points between those is also called as corresponding points. Now we have to allow the light to pass through them according to the Huygens wave theory. Okay, the secondary wavelets are traveling like this, slits, edges, and also they are reaching. We want to focus them on our screen. For example, MN is the screen. We want to focus those one on a particular position. Regarding that one, in the length of the focal plane, focal length, we have to be take one lens. This is a lens. This is a lens, convex lens. Whenever we are using the convex lens, automatically all these rays are focused at the position P naught. They are focused at the position P naught. There we can get the maximum intensity. There we can get the maximum intensity. That's why that is also called as principal maxima or central maxima. There we can get the maximum intensity. Okay. Now, due to the slit edges, secondary wavelets are diffracted. The diffracted wavelets are reaches our screen at the position P1. At the position P1. So there, which type of intensity we can observe, that is depends upon the path reference. Is it or not? So like this position may be called as P1. That position may be called as P1. All these are reaches at the position P1. Now, what is the position of that P1? To know that one, we have to draw a perpendicular line. Why we are drawing the perpendicular line? We have already discussed. So, suppose if we want to calculate the length or path difference between the two waves, it is very simple. We have to draw the normal. Whenever we draw the normal, from that normal, they traveled equal distance, but there is a extra distance is traveled that was given by that normal. So same like that, if we draw the line like this, okay, from here they traveled equal distances. Okay, how much of angle they have diffracted? That is theta. That is also called as angle of diffraction. Okay, now suppose if we take for example this from here to here, this ray and another this ray are participating in the diffraction. Okay, these two are coming from the two slits. That means on the screen here also we can observe not only the diffraction pattern due to the interference pattern due to the number of more than one number of slits. Okay, now we can call this position is called as X. Now Cx is the path reference. What is the path reference? Cx is the path reference. We will calculate that path reference one. path difference. Path difference, what is the path difference here? Cx. How we can calculate this path difference? Simple. That is, this is the theta. Cx we don't know, but hypotenuse AC we know. Okay, whatever the value we want to get. So if we take by using the trigonometry sine theta, we can get that one. Sine theta equals to opposite, that means Cx by hypotenuse. Hypotenuse means AC. Hypotenuse means AC. Sine theta equals to Cx by AC, that equals to Cx by AC, which is equals to AB plus BC. AB plus BC. AB, which is equals to the width of the slit, that is A, and BC, which is equal to the opaque barrier B. That implies path difference. Path difference equals to Cx equals to A plus B into sine theta. Suppose if the secondary wavelets, diffracted wavelets, reaches our screen at the position P1, if they are given the maximum intensity according to the our constructive interference condition, the path difference must be equals to the according to if they are interfere, and if P1 is brightness, the P1 is brightness. So when P1 becomes brightness, constructive interference. What is the condition for the constructive interference? Path difference should be equals to the integral multiple of wavelength. Then only we will get the maximum intensity. But according to our derivation, what we got here? A plus B into sine theta. Therefore, n lambda equals to A plus B into sine theta. That implies, what is our aim by using the grating? We have to determine the wavelength of the source of the light. That means lambda equals to A plus B into sine theta by, here it is multiplying, if it comes this side, it will divide. So lambda by, here simply we can call that A plus B. That means A is the width of the slit and B is the opaque barrier. This is also called as grating element 1 by n equals to 1 by A plus B, say. Then the above equation comes like this. We can write like this: lambda equals to sine theta by capital N into small n. This is the formula for determining the wavelength of the source of the light, where theta is the angle of diffraction, capital N is the grating element. Capital N is the grating element. That means number of slits per inch. The number of slits per inch. Small n is the order of the spectrum. Okay, what is called as spectrum? Spectrum means whenever we are passing the white light into a transparent medium, when it will comes from that medium to the another medium, it will split into 7 colors. Those colors are violet to red, violet, indigo, blue, green, yellow, orange, red. Okay, that is called as grating spectrum. Okay, whenever we are replacing the monochromatic source of light with the white light, in the monochromatic source of light we will get the only spectral lines with a single color, whatever the color we have chosen there. But when come to the white light, we are observing the pattern at the center. At the center, we can get the white light. That is also called as principal maxima or central maxima. That is also called as zero order. That is also called as zero order. From that successive, so for example, I hope you understood this equation. Now, this is the white light passing through the grating. So, like this, if it is coming, so this is called as uh, this is called as principal maxima or zero order. Zero order. So, like that, if we take in this direction, so it may be first order violet to red, first order. Like this, on the both sides we can get first order. This is also first order. Okay, so this is the second order. What is the maximum order possible by using a diffraction grating? What is the maximum order possible by using the diffraction grating? The maximum order possible is maximum order possible. So in this equation, what is the trigonometric term exists is sine. So sine means sine values are becomes when theta equals to 90 degrees. When theta equals to 90 degrees, sine 90 degrees equals to 1. Sine 90 degrees equals to 1. That means therefore lambda equals to 1 by nn. That implies nn lambda equals to 1. That implies order n equals to 1 by n lambda when theta equals to 90 degrees. Suppose if the theta is less than 90 degrees, definitely that should be less than 90 degrees. Why? Because the rays are coming like this, they are falling normally, so 90 degrees means only this is okay. Other than 90 degrees it not be possible. Suppose if that one is theta is less than 90 degrees, the angle of diffraction is less than 90 degrees, therefore the maximum order possible is less than or equals to 1 by capital N into lambda, where n is the number of slits, lambda is the wavelength of the source of light, small n is the maximum order possible. This is the concept about the diffraction grating spectrum, and also the maximum order possible. Please do to subscribe my channel. Thank you.